So here we're talking about the next step in our chemical reactions phase, and that is chemical reactions and sort of generic types. Now there's lots of different types of chemical reactions, and there are lots of reactions that actually fall under more than one type, and we're just going to talk about some of the more major ones, just from a semantics and language sort of standpoint, so you understand when we talk about certain reactions. So the first broad category of reactions we're going to talk about are what are called combustion reactions. So here's one simple combustion reaction. This is the combustion of methane in oxygen, and the two products are carbon dioxide and water. So the combustion of methane in oxygen forming carbon dioxide and water. So the first thing we want to do is balance this chemical equation. So why don't you pause the screencast for a second and balance it on your own. So when I balance it, I get a 1, 2, a 1, and a 2. Wonderful. Here is the combustion of octane. Notice that when I say combustion, which generally means burns in air, the two reactants are the hydrocarbon in question, which is carbon, hydrogen, sometimes an oxygen-containing species, in the presence of oxygen, forming carbon dioxide and water. Again, go ahead, pause the screencast, and balance that chemical equation for extra practice. When I balance the chemical equation, you'll notice that I have a 25 halves here, which is okay. It's not totally bad karma. So we have, if I put a 1 in front of the octane, then I have to put an 8 in front of the carbon dioxide, and then to balance the carbons, and then if I have 18 hydrogens, I have to have 9 in front of the waters, and I have a total of 16 plus 9 is 25 oxygens on the right hand side. And I can get away with writing these 25 halves because that little O2 is there. I still need to indicate that I have 25 oxygens on the left hand side, and I write 25 halves. I don't write 12.5. Convention says we write it as 25 halves just to make it very clear that, oh, yes, I have 25 oxygen atoms on the left-hand side because they're tied up in O2. It's the only real time you can get away with fractions. If you don't like the fractions, go ahead, multiply all those stoichiometric coefficients by 2, and get rid of those fractions. Remember, there's an infinite number of correct answers for any balanced chemical equation. And our last example is C4H10O, again, combustion, and the combustion implies that one of the reactants is oxygen, which comes out of the air, and our products are carbon dioxide and water. Go ahead, pause the screencast, balance that equation. I get 1, 6, 4, and 5. So as you can see, all of these reactions have the same sort of layout. One of the reactants is oxygen, one of the reactants is carbon dioxide, and one of the products is water. All combustion reactions have those three components. Burn in the presence of oxygen, form carbon dioxide, and form water. So now if I were to ask you to draw the combustion reaction for the combustion of, say, hexane, C6H12, you could do it. Just mix it with oxygen, form carbon dioxide and water, and balance the whole thing. So those are combustion reactions. Let's talk about a couple more real quick. We have decomposition reactions, which it's not too big of a stretch. It's something decomposing. So one component falling apart into two or more components. So the decomposition of hydrogen peroxide slowly decomposes into water and oxygen. So it doesn't matter that, there's a 2 there. The idea, the concept of decomposition reaction is there's only one reactant, one single compound. A combination reaction is obviously the opposite of decomposition reaction, where we have 2 or more species coming together to form one product. So there's our ammonia production from nitrogen gas and hydrogen gas, 2 species reacting to form one specific compound as a product. A single replacement reaction is one where you see we have one compound that contains 2 species and one that's sort of by itself, and one of the species sort of swaps out. leaving us with a single product. So for example, hydrochloric acid reacting with magnesium forms magnesium chloride and pure hydrogen gas. So that would be our E in this case. So it's single replacement, so just one element is replaced. Then we have double replacement, where we have sort of like switching of partners, if you will. So we have A mixing with F and D mixing with E. So an example of that would be precipitation reaction of sodium chloride and silver nitrate reacting to form silver chloride and sodium nitrate. And in this case, the nitrate, remember, is sort of its own little group, runs around as a group. So the silver swaps out its nitrate for chloride, and the sodium does the same. So there are the 5 sort of major types of reactions, and again, these types of reactions you can have, especially the combustion, and there are other kinds of reactions, but these are sort of like the basic kinds. And again, this is just sort of for semantics.